Chapter 8, Unit 1. We're going to talk about hypothesis testing. So hypothesis testing uses samples to make educated guesses about the population. The second half of this course is going to consist of learning many different types of hypothesis tests. A hypothesis test is typically used in the context of a research study, and of main interest is using a sample mean to test a hypothesis about a population mean. For this chapter, population parameters, the population mean and standard deviation, are known. So here's an example. So you have a known population before treatment. It has a mean of 16 and a standard deviation of 3. And then you have a treatment. And you don't know what the population mean is going to be after the treatment. That's the goal of inferential hypothesis testing. Let's talk about one basic assumption about the effect of a treatment. If the treatment has any effect, it's simply to add or subtract a constant amount from each individual score. Remember that adding or subtracting a constant shifts the graph, so the mean changes, but the standard deviation, or how variable the graph is, stays the same. Therefore, the assumption is that the population after treatment has the same shape and same standard deviation as the original population. The purpose of research is to determine what would happen if the treatment were administered to every individual in the population. So let's look at an example. Previous research indicates that women wearing red are more attractive. To verify this, researchers conducted a study using waitresses in 5 restaurants wearing the same t-shirts but in 6 different colors, one color for each day of the week over a 6-week period. Results show that male customers tip significantly more if waitresses are wearing red, but there's no change for the females. A repeat study was conducted at a local restaurant. The usual uniform was white shirts and black pants. Tips averaged about 16% of the bill, with a standard deviation of 3. The distribution of tips is roughly normal. During this study, waitresses are asked to wear red shirts. Researchers plan to record tips for a sample of 36 male customers. So if the mean tip is noticeably different, then we'll say wearing red does appear to have an effect on tipping. And if the mean is still around that 16%, then wearing red does not appear to have any effect. So let's look at the 4 steps of hypothesis testing. First off, we're going to state the hypothesis. Then we're going to set the criteria for a decision. Next, we're going to collect data and compute the sample statistics. Finally, we're going to make a decision. In this class, we will be using graphs for every problem that we work. So even if you don't see a graph in your book, know that you need to put one on your test and quizzes. Step 1, state the hypothesis. You're going to always have 2 sides to a hypothesis. The first is the null hypothesis. This says there's no effect, nothing's changed. After treatment, there's no difference at all from the population, so the sample mean is completely the same as the population mean. So the null hypothesis predicts that the IV, or the treatment, has no effect on the DV, which are the scores for the population. Let's talk about the alternate hypothesis, which we call H1. You might also see it written as scientific hypothesis or research hypothesis. This is what the researcher thinks is going to happen. The researcher typically thinks there is an effect. And after treatment, there is a statistically significant difference from the population. So H1, or the alternate hypothesis, predicts that the independent variable does have an effect on the dependent variable. Let's look at step 1 a little closer. State the hypothesis. A non-directional hypothesis states that there is no change or difference. This is what's called a two-tail hypothesis. Basically, the scores are the same as the rest of the people, and they're in the body, or say 95% of the people, you're in the middle there, or you're in the extreme tails. There's no direction stated. It's a two-tail hypothesis. You're either different than everybody else or you're the same as everybody else. In a one-tail hypothesis, this is called a directional hypothesis, then the researcher would state whether they expect the change would be higher or greater than or lower or less than. This graph below shows what your graph would look like if you are saying that you expect scores to be lower. Okay? So therefore, you're either with everybody else or you're extreme and your scores are lower. So let's look at the example that we were talking about before with waitresses wearing red shirts. So your step one, you would just state the null hypothesis, saying there's no difference at all. You'd say the mean of the red shirts is equal to 16. So it's still equal to the same as the rest of the population always. However, the research hypothesis would say that the mean of red shirts is not equal to 16, meaning it's extreme. It's out in the tails, okay? So that's step one. Step two, we're going to state the criteria for a decision. So notice again the graph, and you're going to notice that if the sample means are close to the null hypothesis, then you're going to be in the body. If you're going to be in the tails, those are extreme low probability values if the null is true. So probably the null is not going to be true if you have really extreme values. Remember, the null says you're like everybody else. So if it's not true, that means you're different. So you have extreme values, it's different. So let's talk about the alpha level. This defines a level of significance. It shows the critical regions percent in the tail. It's composed of the extreme sample values that are very unlikely to be obtained if the null hypothesis is true. And it separates the unlikely percent in the tails from the most likely percent of sample means in the body. A probability value that is used to define the concept of very unlikely in a hypothesis test. So if sample data fall in the critical region, then the null hypothesis is rejected. The sample is really different from the population. If sample data do not fall in the critical region, rather they're in the body with everybody else, then the null hypothesis fails to be rejected and we say, oh, you're just like everybody else. The sample is not any different from the population. Common alpha levels that you might see, alpha equals 0.05, alpha equals 0.01, or alpha equals 0.001. So let's talk about boundaries for the critical region. We're going to use the z-tables to determine these boundaries. Example 1. Let's say we're going to use an alpha level of 0.01 and a two-tail test. Since the alpha level of 1% is split between two tails, you divide that in half, that would be 0.5% in each tail. So that would be a corresponding p-value of 0.0050. So basically you take the alpha level, you divide it in half, you determine how much probability is in each tail. Then you look at the tables in the tail column, see if you can find a probability closest to 0.0050. And in this case, you're going to find z-score boundaries, or cutoff scores is what we call them, of plus and minus 2.58. Let's look at example 2. Let's say that we're using an alpha level of 0.001 in a two-tail test. And again, this is 0.1%. You're going to split it between two tails. That's 0.05% for each tail. To determine the boundaries, you're going to look up the p-value of 0.0005 in the tail to determine z-score boundaries of plus and minus 3.30. And again, this alpha level of 0.001, this means 99.9% of the scores are in the body with everybody else. Only 0.1% is in the two tails. Finally, example 3. Let's use an alpha level of 0.05. This is probably most common, and most of the examples in your textbook will use this alpha level. It's a two-tail test. It's going to split the 5% between the two tails. That's 2.5% per tail. So to determine the boundaries, you're going to look up p-value of 0.0250 in the tail column, and you're going to find z-score boundaries of plus and minus 1.96. So let's look at what this looks like on your graph, because for every problem, you're going to have to draw a graph. Okay, so you have the middle 95% of values, because if alpha level is 0.05, that means 5% are in the tails. That means 95% is in the body in the middle. Okay, and so the alpha level, if you color in the rejection regions there on either side of those boundaries of z equals plus and minus 1.96 lines, those are the extreme regions. Those are the rejection regions. If you're in those rejection regions, you're going to reject the null and say, no, I'm not like everybody else. If you fail to reject the null, then you're in the middle. You're going to be like everybody else. So step 3, you're going to collect data and compute sample statistics. You've been doing this already, so you know how to do this. We're going to calculate a z-score. So there's the equation for a z-score. Z is equal to, again, just the sample mean minus the hypothesized population mean over the standard error between m and mu. So in this example, let's say for the original problem, the mean was 16% for the tip rate. Let's say we had 36 people in the study with a standard deviation of 3. Well, suppose the sample produced a mean tip of m equals 17.2%. Let's see if it's different or not. So you're going to compute the standard error. You should get 0.5. And then you're going to compute the z-score. Filling in what you know, you're going to get a z-score of 2.4. So that's step 3. You simply do the calculations. You calculate z. So we're going to talk about how we make our decision. So here's our same graph we had from before. I want you to put an X on the graph showing where the calculated z-score was located. Remember, it was a z of 2.4. If X is located in the critical region, then we reject the null hypothesis. We say, hey, we're not like everybody else. We're rejecting the statement that says we are. If X is located in the body with the other 95% of the scores, we're going to fail to reject the null hypothesis. Remember, the null says there is no change. In this problem, z equals 2.40, so X is in the rejection region, actually because z calculated is much greater than the cutoff score of z of 1.96. Your conclusion is to reject the null. Let's talk about how you'd write this up for a journal. You would say, waitresses wearing red shirts earn significantly different tips. And how do we know this? Because we calculated a z-score of 2.4. The probability of us getting this z-score is less than 0.05. When you're in the rejection regions, we say less than because you're in that less than 5% chance of being there. Notice we don't say higher tips because we did not do a one-tail test. We used a two-tail, which only tests for differences. Use z calculated when writing the conclusion. Never use the cutoff z-scores found in the tables. You would never say z equals plus 1.96. You would always use the calculated z-score. That's the #1 issue people have when they're solving problems. Remember, there's a 5% chance of error. The error is equal to the alpha level. So we are 95% confident in our decision. When the probability is less than the alpha level and the null is rejected, we write probability is less than whatever the alpha level is, in this case 0.05. When the probability is greater than the alpha level, this is when z calculated puts the score in the body with the other 95% of the scores, we would fail to reject the null and we would write the probability is greater than the alpha level, okay, because you're in there with the other 95% of the people. It's a really high probability you'll be there. Let's look at an example. A normal population has a mean of 40 and a standard deviation of 8. After a treatment is administered to a sample of n equals 16 individuals from the population, the sample mean is found to be m equals 45. Using an alpha level of 0.05, is there a treatment effect? Step 1, write the hypotheses. No direction is given, so we use the hypotheses for a two-tail test. So the null hypothesis is, yes, the mean is equal to 40, and the research hypothesis says the mean is not equal to 40. Step 2, set the criteria. It's a two-tail test, so you divide the alpha level in half to determine the probability for each tail. So this leaves us with 2.5% probability for each tail. You look in the tail column, find the p-value closest to 0.0250, and you're going to find z-scores equal to 1.96 from your table. Draw the picture, draw your lines at the cutoff scores of 1.96, positive and negative side, and then you shade the areas. Next, you're going to compute the sample statistics for the problem. So I found an estimated standard error of 8 over square root of 16, which gave me 2. Then you're going to calculate the z-score. So 45 minus 40 divided by 2 is going to give you plus 2.5. Then I want you to make a table using your standard error and the estimated mean, which is 40. Then I want you to make a decision. Put the X on the graph for where you calculated your z-score. Well, you calculated 2.5. Since you're in the rejection region, you're going to reject the null. There is a significant treatment effect. Z is equal to plus 2.5. The probability is less than 0.05. Hypothesis test versus jury trials. A test begins with a null hypothesis stating there is no treatment effect. A trial begins with a null hypothesis that you are innocent until proven guilty. Research study gathers evidence to test whether the treatment has an effect. Police gather evidence to test whether the accused actually committed a crime. If there's enough evidence, you reject the null hypothesis and conclude that there is evidence for a treatment effect. If there's enough evidence in a trial, jury rejects the hypothesis and concludes that the defendant is guilty of a crime. If there's not enough evidence, the researcher fails to reject the null hypothesis. The researcher does not conclude that there is no treatment effect, simply that there's not enough evidence to conclude there is a treatment effect. You never say accept because there's always a chance of error. You always say fail to reject. In a jury, if there's not enough evidence, the jury does not conclude that the defendant is innocent. They just simply say there's not enough evidence for a guilty verdict. Let's talk about the Z-score formula as a recipe. So the Z-score formula is like a recipe you can follow, and the formula produces a Z-score. In the hypothesis testing situation, you don't always have the necessary ingredients. Many times you do not have the value for the population mean. So here's a recipe analogy. So you're trying to make a cake and there's a grease stain on the page and you can't tell how much flour to use. So one, you make a hypothesis about the amount of flour. In this case, we're going to assume 2 cups. You test your hypothesis using the 2 cups of flour and bake the cake. If the cake is good, you assume your hypothesis is correct. If the cake is terrible, you assume your hypothesis is wrong. So in Z-score, here are the steps. You make a hypothesis about the value of the mean. This is the null hypothesis. You plug the hypothesized value into the formula along with other values which are similar to ingredients. If the formula produces a Z-score near 0, you conclude the hypothesis was correct. If the formula produces an extreme value, we conclude that the null hypothesis was wrong. Let's look at the Z-score formula as a ratio. So we know that Z is equal to M minus mu over standard error. It can also be written as sample mean minus hypothesized population mean divided by standard error between M and mu. It can also be written as the actual difference between the sample M and hypothesis mu over the expected difference between M and mu with no treatment effect. So an example, a Z-score of +3 means that the obtained difference between the sample and the hypothesis is 3 times bigger than would be expected if the treatment had no effect. A large Z-score indicates a large discrepancy between the observed sample data and the sample data we would expect based on the null hypothesis. A large Z-score value indicates that the sample data are very unlikely to have occurred by chance alone. The values are so extreme that the treatment probably did make a difference. So here's learning check problem 1. In general terms, what is a hypothesis test? See if you can figure it out. So hypothesis test is an inferential technique that uses the data from a sample to draw inferences about a population. Remember, descriptive techniques are what we use on samples, but when we do the hypothesis test, we're going to use inferential techniques and infer the information from the sample to a population. Learning check problem 2. A sample is selected from a population with a mean of 75 and a treatment is administered to the individuals in the sample. If a hypothesis test is used to evaluate the treatment effect, then what is the correct statement of the null hypothesis? You should have gotten mean equals 75. Which of the following accurately describes the critical region for a hypothesis test? So if you look at the graph that we had talked about previously in class, you can tell that outcomes have a very low probability if the null hypothesis is true. Learning check problem 4. The psychology department is gradually changing its curriculum by increasing the number of online course offerings. To evaluate the effectiveness of this change, a random sample of 36 students who registered for introductory psychology is placed in the online version of the course. At the end of the semester, all students take the same final exam. The average score for the sample is M equals 76. For the general population of students taking the traditional lecture class, the final exam scores form a normal distribution with the mean of 71 and a standard deviation of 12. Which of the following correctly describes the outcome of the hypothesis test? Well, first we have to solve this problem. Step 1, write the hypothesis. Again, no direction is given, so we use a hypothesis for a two-tailed test. So the null hypothesis just says everything's the same, the mean is equal to 71. The research hypothesis says the mean is not equal to 71. Step 2, we're going to set up the criteria, two-tailed test, using an alpha level of 0.05. And again, this gives us z-scores of plus and minus 1.96 when we look in the tables. We draw the picture, we shade the tails. The shaded area is going to be the rejection region. Next, we're going to compute sample statistics. So find the estimated standard error. I found it to be 2. Calculate your z-score. I found it to be 2.5. And then you're going to make a table using your standard error of 2 and using your estimated mean of 71. Step 4, you're going to make a decision. Place an X on the graph for the calculated z-score you got of 2.5. Since this is in the rejection region, we reject the null. There is a significant treatment effect. Z is equal to plus 2.5. The probability is less than 0.05.